Hi, my name is Martin Beracochea, and I work in the microbiome informatics team in EMBL-EBI. And today I'm going to be speaking about metagenomic data analysis workflows in CWL, basically from scratch to a multi-environment production. First, I would like to start with a talk overview of the different points I'm going to be discussing today. I would like to give a brief introduction to what is metagenomics and what is MGnify. Then I will continue talking about a little bit about how MGnify has been evolving for the past few years and how this evolution has led us to the common workflow language. And then I'm going to speak a little bit about how the common workflow language and how we are using it in MGnify. And finally, I want to talk about our experiences deploying our different MGnify pipelines in different cloud environments. First, I would like to say that metagenomics is a really broad term that has been used for many different things, but basically it's basically try to understand the sum of the genetic material in an environmental sample. So there's multiple reasons people who may want to do that. For example, maybe the most classic example is try to understand all the microbiota that lives in the gut of humans, because that has many different implications in human health and it's related to some diseases. But it's also been involved in different environments, and it has in the recent year has been involved, for example, in the industry, where maybe the oil industry is interested pretty much in metagenomics, because, for example, in some pipes, some of these bacteria or different microorganisms may form biofilms in some pipes, and that costs basically a lot of money for them. So they are quite interested in that. Metagenomics is also used as an umbrella term, and maybe in the most traditional sense, it was basically from an environmental sample. Basically, in the lab, one may do a size fractioning and get traditionally the bacteria fraction of that, and then it will extract all the DNA from there, and they use maybe maybe we'll try to get a marker gene, and we'll sequence all the DNA using after a PCR and get all that data for a taxonomic profiling. This has been shifting over the past few years with the introduction of different DNA sequencing technology that are more powerful and they are less expensive. So, for example, one may be interested in sequencing all the DNA in a sample, not just the prokaryote fraction. Maybe or one is interested in analyzing all the viruses there. So you can do that now. It's easier to do. Another dimension to this is the methodology that one may use to analyze this. For example, one may extract all the DNA and then do a shotgun sequencing of all the DNA there. That would be metagenomics. But then one also can extract the RNA there and have a metatranscriptome. So there are different approaches that everything is used. Everything is taken under the umbrella of metagenomics. And even in the last few years, has been the long read DNA sequencing technology has been used for metagenomics more and more. As I mentioned before, I work on the MGnify team. We are responsible for the MGnify resource. This is basically a hub of data, of metagenomics data. Basically, people can actually see, assembly, analyze, and we are responsible for the assembly, analysis, and archiving of microbiome data. So basically, we can we have our own set of standardized high performance pipelines to analyze data that people may submit for us to analyze. So we usually take public data sets and analyze that information and then make that information publicly available for the community. So it's not ADP, it's more like a resource. So basically, if anyone is interested in having their metagenomic data to be analyzed, they can send us the data to us and we can analyze that for them. MGnify has been around for a couple of years. So we have several versions of our different pipelines. And over the year, the pipeline has been evolving, and it's been we have seen an increase on the complexity of the pipeline. So this evolution basically has made us swift a bit of the tools we are using to that. For example, as an example, I'm going to compare the latest version of the pipeline with the previous version. So the previous version is version 4.1. It was released in January 2018, and it's not really a complex pipeline. It basically has some quality control steps, basically from the raw data that we are sent. Then basically has some RNA and taxonomic profiling of that information. So this has been available, and we will be using this for the last year or so, and then we've switched to the version 5 that was released a year ago. And as you can see, the complexity of the pipeline has increased a lot. Basically, we have 3 different subversions of the pipeline that I don't have the time to go into too much detail today, but I'm happy to discuss that if you want to. So as you can see, compared to version 4.1, the complexity of the pipeline has increased dramatically, I would say. So we needed a way of coping with this complexity, because we have, for this version of the pipeline, we have over 20 different applications. Everything, all of them are interconnected and they talk to each other. And basically we have a really diverse set of different runtimes, dependencies that collide with each other. And over the year, we decided to drop our code base for version 4.1. The code base for version 4.1 was basically a Python code base that was extremely difficult to maintain, an extent of nearly 10,000 lines of Python code that was really tightly coupled to our own cluster infrastructure. So it's really, it was impossible to cope with the complexity of version 5 without code base. So we wanted to move to a different platform to actually try to build this new version of the pipeline much easily. And also we wanted to have some, so as we provide a service to the public, we also wanted to do this in a standard way. So we wanted to improve the reproducibility of our pipeline, because with the version 4.1, it was nearly impossible to run that outside the EBI cluster, so we couldn't share the pipeline with other people. And we also wanted to improve the provenance of all of the different output files we produce. So basically, we wanted to track back for any given output file of a pipeline, how that file was actually produced, to improve the interoperability, reproducibility of our pipeline. So with all of this in mind, we started to move to the common workflow language, as we saw this as an opportunity. And so we dive into the language straight away. So first of all, I would like to briefly introduce the common workflow language. It's a declarative way of defining a pipeline, how the data basically flows between different command line applications. So basically, you don't have to code, you declare what you want to do, and then you let CWL to do that for you. it's important. It was important for us that this was actually a standard. This is a standard developed by the community. It has a well-defined schema. It has a specification, and it even has a test suite. And also, one of the things that caught our attention is that it supports containers. So having all of those different tools installed was really complicated. So basically, just by moving to containers, made our life really less of a hell, I would say. How how do you define a CWL pipeline, basically, or a workflow? Okay, so the first item that you need to do, basically, each command line CWL file is a YAML file. It's a plain text file based on the YAML. It's a YAML-based source code, basically. So with a text editor, you're good to go, and you can start writing your own command line tool wrappers and your different workflows. Basically, each command line tool that you write, it has to have a file type and a metadata. Basically, you need to specify which version of the standard you are trying to use. Then you define for a tool, for example, you will need to find that is a command line tool. What is the actual executable file that this CWL wrapper is going to execute? In this case, it's just a Python script that is going to filter some context, apparently. Then you will need to define the inputs of that tool and the outputs. And for each input, you will define what type of data it is. On this guy, for example, the FASTA file is a file, and you then will bind the different parameters of this script, and you will need to you will specify all the different options on the input section of the file, and then the output of this file. So you end up writing the command line definition for each one of your tools, and then you will need to connect those using a workflow, a CWL workflow. What does look a workflow in CWL? It's the same. It's a YAML-based file again, but you will need to specify a class workflow, and it has the same structure. You have inputs for that workflow, and then you have outputs. And basically, for a workflow, you will define steps. For example, for this one, and the input section, you see that this one receives an input FASTA file, and then a flag called build sorted biome that is a Boolean, so it's a true or false. And then you will feed those input files to the different steps. And then basically you connect the different steps using the different outputs of the different steps. Basically, step one is going to process the file in a way, and then that output of the step number one is going to be fed to step two, and so on. So basically, CWL is going to work out how to execute that for you, so you don't have to worry about that. You just feed the workflow with the inputs, and then you get out your outputs. One of the main advantages of using CWL is basically that you can, if you work and if you write your workflow clever enough, you can reuse different bits, and you can actually reuse maybe some workflows that you may find from other teams, or even on that someone can actually provide you. For example, on our case, we were able to run sub workflow for MGnify. This is another metagenomics platform. But for our case, when we have different flavors of our pipeline, we can compose our pipeline from the ground up, and then we can reuse different components, so we don't have to be writing again. We can reuse those bits, and we can just say, okay, well, let's plug and play the different components that we want, and we can change the flags, and that's it. It's important to know that CWL is just the way you describe your workflows. Then you will need some engine to actually to execute that. So the first step is you write all your different command line wrappers in CWL, and then you define how your workflows look like. Then you will need someone to actually execute that for you. There are several different implementations of CWL. You have the reference one, that is CWL tool, but for a HPC kind of environment, this won't work because it's basically running one task after the other, and it won't be able to reuse, for example, a work schedule on a cluster or something like that. So as we in EBI have a cluster that is using IBM Spectrum LSF, we went to with CWL exec that is actually developed by IBM. So that's our first try to run a pipeline was using this one, but we bumped into an issue. This engine wasn't being actively developed, and it has a limit of how many jobs in parallel you can run. So that was a no for us, basically. So you have to keep in mind that not every one of the CWL implementations out there will work for you. So we decided to go with one named Toil. That is, and Toil basically has the features that we are looking for. We needed something that is able to talk with LSF because that's what we have in EBI cluster. So that was a requirement for us. And we also wanted to have support for the containers. As in many other HPC clusters, running containers using Docker is not allowed because of security concerns. So basically, we needed to support Singularity. That's another more HPC-friendly container engine. So Toil supports that. So that was a good thing for us. So Toil has been our CWL runner for the past year. And it also supports other workload management as Slurm, so that was a nice thing to have. How has been our journey with Toil? This is not, the idea of this is not to code shame or Toil, because the Toil team is been great for us and we work close with them. But the Toil adoption of CWL is fairly recent, so we bump a lot of different bugs along the way that we have been fixing with the Toil team. So it's not really, it wasn't the best experience at the beginning, but we managed to overcome some of the issues. But keep in mind that working maybe with CWL and Toil is not as fast as maybe with other engines. I work a little bit with Nextflow, for example, and I feel like working with Nextflow is a bit faster on the development process. That I would say keep that in mind. Maybe Toil logs are extremely verbose, and it's really complicated to debug errors you may encounter when your pipeline is working. So this is another thing we are working with the Toil team to improve. Also, we bump into some issues with the communication of Toil and LSF with different versions of LSF. We were bumping that Toil wasn't communicating as it should, so some job was failing and it was kind of tricky to debug. And also, our pipeline is relatively complex compared to other pipelines out there. So there were some other issues with the Toil interpretation of the workflows. So, but I'm happy to say that over time we managed to overcome some of those issues, and Toil is working really well for us at the moment. But it was a bumpy road. So we had our pipeline, we had Toil, and we were able to run our different pipelines in the EBI cluster using Toil. But then we noticed that some of the tools weren't actually scaling up to our expectations, because as we provide a public service that's really generalistic, we get some of the samples that we get are fairly big. So, for example, Hammer or Anti-Smash, those two components of the pipeline, were actually coping with that, and they were taking a long time because our internal parallelization mechanism wasn't good enough. So what we did is we taking that into our hands, and basically we're splitting files and trying to horizontally scale that for us. So keeping that in mind that some of bioinformatics tools out there may not perform as you expect at scale. So be prepared to do some digging by yourself if you plan to do this. So we had a pipeline working on EBI cluster. It was performing as we expected. We were really happy with it. So we told ourselves, okay, so we need to move this to the cloud, because there's some advantages for us to moving into the cloud, because sometimes the cluster may be cluttered with all the different people that's trying to do stuff on the cluster. So, okay, we need to move to try and define an architecture that will work for us in the cluster, in a cloud environment. So we went to the common lowest denominator for us. It's basically, by using TOIL and CWL, we had most of the components needed to run it on the cloud, because TOILs and CWL will interact with our code base, and they can interact with, for example, LSF or SLAM to distribute the workload across. For example, if we define a setup with master and workers on the cloud, basically using virtual machines, we can distribute the work, and we can use LSF or SLAM to actually do that for us. So we didn't have to do anything else, because TOIL and CWL were already doing that for us. So with a fairly simple way of providing a close as to the HPC EBI HPC cluster, we can replicate that into I would say any cloud environment. So far, we have tried with Oracle infrastructure, cloud infrastructure. We have tried with Embassy Cloud. This is EBI OpenStack platform, and also recently we have been fiddling with Google Cloud Platform. So basically, the only thing that we actually needed to write was a Terraform way of a set of Terraform scripts to provide all the infrastructure and any of the different cloud providers that Terraform supports. But also, when you run things on the cloud, you would expect everything to be great, and then you run things and you get your output and everyone's happy. No, that's not the way it worked for us. We, for example, run two different projects with Oracle Cloud Infrastructure. The first was actually to run a memory-intensive step of our pipeline on Oracle Cloud Infrastructure, and we bump into a obscure kernel issue in Oracle Linux that took a good month to try and find out what was going on. So then after that, we learned that we should use CentOS for R, because that's the Linux distribution that we're using in the cluster. So bear that in mind to try to keep everything as close to what it works. And then, on the good side, we ran a second project to compare how OSCE was compared to the cluster using some of the bare metal instances that the Oracle folks provide, and we found that it really increases our throughput. So that's a really good advantage. So take advantage of the different opportunities the different cloud providers may provide you. And then, as a summary, I would say we end up with a really good CWL-based metagenomic pipeline. We are really happy with it. We managed to build our deployment process in such a way that using Terraform only, we can actually deploy our pipeline and run them on some of the cloud providers out there. We have tested this with Oracle, also with OpenStack API OpenStack platform, and with GCP recently. And on the future things that we are working on, it's basically, at the moment, we haven't decided how we are going to do with the data flows of files, inputs or outputs, how we are going to keep everything, because at some point we need to get all of that into the EBI cluster to archiving. We also need to work on the job packing and trying to improve things, because as you move into the cloud, you want to be as optimal as you want to spend less money, basically. And how we can orchestrate between different environments, given the case we run things on Embassy or on GCP at the same time. You don't want to be running the same jobs on those different clouds. And lastly, I would just like to thank you, everyone at MGnify team, Profin, that is the team leader, our cloud consultants and ABI, Tony Waldish, especially, that's been helping us a lot, and other demonstrators, Alex Silva, that has been really helpful. And on the CWL side, Microsoft has been a great help for us. Thank you.